Hello, everyone. Now we come to the part of hands-on on histogram and pie chart. So we have this example here. So we have this data set where we have two features or two fields. One is a numerical field, which is the score, and the other one is a categorical field, the subject field. So we're going to plot the histogram for both of them and the pie chart for the categorical one. And we're going to play with different parameters, okay? Let's look at this cell here. So here we are defining both these two variables. They are defined as lists, okay? So this is the first list, okay, which is the categorical variable, and this is the second list, which is the numerical variable. This line here we have at the beginning, this just to guide Jupyter Notebook to show the figure right below the cell. So in order to plot the histogram and the pie chart, we need to use this library and specifically this module inside Matplotlib library. So we we import matplotlib.pyplot as PLT. So we're going to use this model because the functions that are used to plot the histogram and pie chart are inside this module. So here, the first thing we are creating the figure. This just creates the figure, okay, this line. We can specify the size of the figure. Here, 5 by 5. I think it's a 5 centimeter by 5 centimeter. As I said, this just defines the figure, okay? The actual plotting of the content is happening at this line here. So we call the function hist to plot the histogram, and we pass the variable here. So we are plotting the histogram for the first, now for this, in this cell, we are plotting the histogram of subject, which is a categorical variable. Then we call the function show function, so plt.show, in order to show the figure below the cell. Okay, so if we run this, okay, this is what we get. Okay, 3 vertical bars. The order is as they appear here. M is the first one, P is the second one, and C is the third one. And the bar, the height of the bar reflects the number of occurrences for every one of them. Physics is the mode here, the one that has the highest bar, or the one that has the highest frequency of occurrence. Now we come to the second variable, which is a categorical variable, score variable. So we're plotting the histogram for that one. So there are two differences compared to the categorical one, okay? Since the real line has infinite numbers, we have to define bins, as I said. So we have to define bins. We cannot plot for every variable there because there are infinitely many values, okay? In the range of this data, which starts at 71, the minimum is 71 and the maximum is, I think, is 100, okay? So then we need to define bins. There are two ways to define a bin or define bins, okay? So we can, first way is you actually pass the exact cutoff points inside brackets. So the first point is the starting point, and the last point is the ending point, and the points in the middle are the cutoffs between the starting and the ending point. Okay, so we start at 71 and we end at 100, and we have two other cuts in the middle, one at 81 and one at 91. So we pass them comma separated inside brackets. So with that, we are defining how many bins? We are defining 3 bins. The first bin takes values from 71 to 80. The second bin takes values from 81 to 90. And the third bin takes values from 91 to 100. So we are passing, we're like adding this argument here in the histogram, okay, in this function. So we pass the variable and this extra argument in order to define the bins. That is how we now we define it three bins here. As I said, we pass the starting and the ending and the cutoff points. So the second difference is that, as we can see here, it's like the bars, the ending of the first bar is the starting point of the second bar. Okay, so it's continuous in that sense compared to here. We are representing different categories. Okay, these are the two differences. We can also now here, as I said, this is one way to define uh, like how many bins you want to have and where you want to cut. Okay, that's one way to do it. But if you want to, for example, like, for example, if you are passing a large number of pins, it will be like too much work here in order to pass the cutoff of every bin. Then actually you can just pass the number of pins here, like in this example here. Okay, here we define bins is equal to 30. So we want to generate 30 bins. Okay, we want to split that segment from 70 to 100 or 71 to 100 into 30 bins. Okay, uh, so then what happens behind the scene, Python will find the minimum and the maximum, and then we'll split that range into 30 equal bins. Okay, so there will be more bins compared to this. Here, there used to be only three. Now there are 30 bins. Okay, so then the width of every bin will be much small, and we may actually encounter some bins where there are no occurrences or the bars, there are no bars. Okay, the height of the bar is zero. So as we can see here, okay, so there are no numbers in this range. Okay, so there could be here 2, 3 bins. Okay, but none of these bins have any of the occurrences here. Their numbers, the numbers inside the range inside that bin has no number that is exist here in this list. Okay, so yeah, so that's the histogram of the score when we define 30 bins or buckets. Now we come to the uh, pie chart. Okay, so here for in order to plot the pie chart, as I already mentioned, for pie chart we are plotting the proportion or the percentage. We're not plotting the exact frequency or count. Okay, we're not plotting counts. Okay, we are plotting proportions or percentages. So then we need to compute those. Uh, we don't need to compute it. This is what's gonna be actually computed by Python. Okay, so what we need to extract are the different labels and the counts. Okay, so for every label, and as I said, this is for pie chart is for categorical type of data. So here we are extracting from the input list subject. Okay, we are calling this function here. We're going to come to that. So from subject, from our input list, we are extracting two things, the labels and the counts. That's all we need to plot the pie chart. So in order to extract these two, we are calling this function np unique. We're passing the list as an input, though this is numpy array. Okay, this is inside this function. I mean, unique is inside the uh, inside the numpy library. Sorry. Okay, but we are passing a list here, and it's still going to do the same thing. I think behind the scene is converting this to a numpy array and then performing the function, because actually we don't need, as you can see, this line is commented out. So here we created an array and then we used to pass that array, but actually you didn't need to. If you pass the list, it's still gonna work, the function. Okay, it's inside NP library, NumPy library, but it still can take a list as an input. So we're passing subject here. Okay, by default, if this line is not there, okay, let me maybe copy this here. Okay, Let me do it first of all without this. Okay. So then it will return only one variable. Okay. By default, it will return the labels unique. So it's gonna go through the elements and takes like how many unique values there. What I mean by that, so math M happens many times. It's just gonna take the first occurrence for M, then goes like physics or P. Now we have M, P, and C, right? So it will count. It will extract one M, one P, and one C. Okay, it's gonna represent those repeated M's by only one M, repeated P by only one P, and repeated C's by only one C. So in other words, it's gonna extract the labels. It's gonna return how many different categories are there, okay? Or different, like, yeah, how many different categories are there. So it's not gonna return how many, it's gonna return the values of those elements or categories, okay, which are strings here or characters, okay. So then the labels will be, so we will have three labels. I think they will be sorted alphabetically. So C will be first, and then M, and then P. Let's run this, and but look only on, for the first this one. So we have, okay. I don't want to go beyond. Okay, maybe. Oh, let me just. Maybe I should have actually run this in a different cell. Okay, Command X. Let me add another cell here. Okay. Okay. Oh, okay. So I need to print the labels. Okay. So this is what we get. Okay. C, M, and P. They are alphabetically ordered. Okay. That is if we are actually, as I said, if we are only, yeah, if we are passing subject. Now with this extra argument here, we pass. Let me zoom in again. Now, with this extra argument we pass here, returning counts is equal to true, because here, if we don't pass in a value for that argument, then the default value will be taken, and the default value for returning count is equal to false. Okay, so then it will not, this function will not return the counts. Okay, it will return only the labels. But if you want the counts, and we need the counts to plot the pie chart plot, so in order for that, then in order to get that, we need to pass this argument. So return counts is equal to true. Now, the function will return two variables. So we need to we need to define two variables here, which are the labels and the counts. Now we're gonna get both the labels and the counts. So if I run this cell, so here we're getting both the labels and the corresponding counts. Okay. Then we can now call import the matplot lib.py plot and plot the pie chart. So here is how we plot the pie chart. We call the function pie. We pass both. Okay, we pass both the counts and the labels. Okay, and this is just for the sake of presentation. So we for the percentage, we need to consider two digits after the decimal point. Okay, so then running this is what we get here. Okay, so the percentage of every one. Okay, and the size of the size of the sector depends on the percentage. So the higher the percentage, the higher is the sector, and they have to sum to 100 because these are percentages, and the labels are printed as you can see here, and these are the percentages. The percentages are printed inside the sectors, and the labels are outside. Okay, so what if we don't know the function unique? Okay, we still can do it. We can, there are different ways here commented. I will just go very quickly over some of them. For example, here, maybe this is the first order way that comes to your mind. If you don't know this function, you just initialize three counters to 0. Okay, each counter represents the number of occurrences for one of these three categories, and then you loop through the elements. Okay, and you insert this condition here. Okay, if you encounter M, then you increment the counter of M by 1, and the same for the other categories. So then you will retrieve the counts, and then you have the counts and the labels. You call the pi function in order to plot the pie chart. Okay, you can also use the count function, which is like inside the object. This is a list, so we can call dot count and pass the value of the element that we want to retrieve its count. Okay, so here for M, then we will retrieve the number of times that M has occurred there. Okay, we can also do it this way. Okay, so maybe this is like this way is a concise or compact way of compared to this one. So we start with an empty list, okay, and then we loop over the labels. We have 3 labels, and we append to that list the sum of the occurrences of that label in the array. Okay, here we are looping in the array, so we need to define this array here. Okay, this one. Need to cast or convert the list to an array. Okay, so we're appending what? Whenever the value is equal to this label, okay, this is the return of this array of booleans. Okay, so then you sum all truths that will be the a number of occurrences for that specific label. Okay, and you can also call the function set here. Okay, that will return, I think, no, that returns the labels. Yes, yeah, that returns the labels. Yeah, so here you return the counts using this or this. You return the counts, and then you can return the labels calling the function set. Okay, but when you call the function set, you return the labels as a set. Okay, this is not a list. This is a set. Okay, now these are like just other different ways to extract or to compute and find the labels and the counts in order to plot the pie chart. Okay, so now we come to the normal distribution. We have already talked about normal distribution in our Python review, but let's go over it once more. First of all, let's read through these lines and try to explain them. So a histogram depicts the distribution of the variable. So from the histogram, looking visually into the histogram, you can, for example, you can actually approximate or estimate, or you can, it's not really estimate, you can actually, how to say it, you can tell it's closer to which kind of distribution. Okay, what is the distribution of the data? For example, looking into this seems to be following a normal distribution. Okay, by just looking at the histogram, I can tell that. If I want to approximate it with one of the well-known distributions, then the best approximate for this is the normal distribution. It's definitely not a uniform distribution. Okay, it's much closer to the normal distribution. A variable's distribution may not be easy to estimate, because actually in order to estimate the distribution of a variable, you need infinite number of samples, and that may not be, because you need to cover all the range. Okay, so that may not be practically possible. Okay, available, I mean, the infinite number of samples. However, it can be easy to check if it's closer to a particular distribution. This is just what I explained. One of the well-known distributions is the normal distribution. Okay, so this is, as I said, this is the shape of the normal distribution. So if you plot a vertical line here in the middle, you'll see symmetry to the right and left. Basically, the normal distribution, like in normal distribution, there's like a point with the highest probability. Okay, and as you go to the right and left, the probability decreases following the shape of the normal distribution or the Gaussian distribution. That's the normal distribution. That's defined by mu and sigma. Mu is the actual mean or the expected value, and sigma is the standard deviation, which is the square root of the variance. Okay, so the normal distribution is defined by these two variables. Mu defines the center of the distribution. Higher mu just shifts the center. So if higher, like a different mu can have different centers, but they what controls the shape? Let me maybe plot it here. It's easier. Okay, very quickly. Okay, so let's draw here. So let's have, okay. So here, this is a Gaussian distribution with mu equal to 0. So this is with mean 0. And this is also Gaussian distribution, but with mean equal, for example, 10. Okay. So mu, or the mean, okay, defines the center of the distribution. And sigma defines the dispersion around the center. So higher, for example, if we look at these two distributions now, okay, let's look at this one. This is one, and this is another one, okay? Okay, which one would you expect that have higher sigma? It's the second one, okay? Second one, sigma 2 is greater than sigma 1. So higher value of sigma leads to more dispersion, okay? So as I said, mu controls the center and sigma controls the dispersion, okay? We can have also positively skewed as well as negatively skewed normal distributions. This is how the positively one would look like. There will be a tail. So if you plot if you look at the right side, it follows exactly the normal distribution. So you see this tail behavior here, while in the left side, it's cut off very early. And in the negative skewed, it's the other way around. So for looking at the negative part for the left part, sorry. So the left part. So here the right part, and here the left part. The left part follows the normal distribution, and the right part is cut off early on. Okay. Yeah, this is like these are the positively and negatively skewed normal or Gaussian distributions.